And let's wait a couple minutes to make sure we got everybody in here. Got a couple here still trying to get in, so. All right. Okay. Well, yeah, still got a few coming in, so bear with me. All right, looks like everybody's in now. Well, welcome to Chem 130 at SCC. My name is Dr. Fred. I will be your instructor this semester. Obviously, online class. All the lectures will be online. But before I begin, let me take roll. Let me find out who's here, who's not. As I call your name off, if you would, in the chat, please type your name in. It gives me a hard copy of that you're here. So apologize early if I misspell your or mispronounce your name. I try not to kill it too bad, okay? All right, how about Eli Alonso? Are you here today? Alonso, Eli. No, okay. All right, how about Davey Bach? Dave, oh, there you go, Dave. All right, you go by Dave or Davey? I got Davey listed here. Either, okay. All right, and how about Derek Boone? Here, got you. All right, Carissa Capriotti. Carissa, are you here? No. Okay, how about Natalie Kobe? Natalie, gotcha. Jennifer Demasio. Jennifer, yeah, gotcha. How about Amaya Ellis? Amaya? Yeah, here, I got you. Okay, Funny Ron, last name. Got you. How about Edwin Gomez? Edwin, you here? Okay. Gonzalez, Yasaria. Nope. Okay. Elisette Hayes. Gotcha. Thank you. Is that Shani, or how do you pronounce that? Hockey, last name Hockey. Shani. Okay, got you. Max Hopfinger. Max, got you. About Isaiah Hun, I believe. Hun. Present, catch. About Jacob Jerome. Okay, Jacob. About Ezra Kingswaba. Got you. And Jacqueline Lipscomb. Here. Daniel McDevitt. Got you, Daniel. Emma Nelson. Emma. Okay, not here. Alisa Ortez. Lisa. How about Tyler Russ? Tyler Russ right here. How about Tyler Slaney? Okay. And how about Angela Turney? Angela? No. And Celine. Jaghar, really? Celine, good. All right. So, let me see. The people that I do not have that were on my list are Eli Alonso, Carissa Capritrio, Gonzalez Lahadia Gonzalez, Emma Nelson, and Angela Turney. Okay, Eli, I got you. I see you here. Okay, anybody I missed? I just downloaded. This is the latest list I have. Okay, let's see Carissa. Carissa just joined us. All right. Well, I want to thank you for bearing with me for a second, because I am at the tailor end, at the far end of dealing with the corona. I tested positive and a little bit of short of breath. So we're gonna probably take a little extra break, more so than normal. So, all righty. Again, my name is Dr. Fred. Normally, if we were doing this live on campus, we'd be having the labs in the morning and then the lecture here in the afternoon, like we're doing this. So, but we're not. So we're going to do online lectures. So here's the thing. I teach at 2 places. I teach here at SCC. I also teach at GCC. With that being said, and that's Tuesday and Thursday, and I'll send an email out to you. You are more than welcome to attend my Tuesday, Thursday classes. They're from 3 to 4:15 to give you an additional resource as far, because both classes, we use the same lecture books. We use the same textbooks, I should say. Literally going, it's the same class. It just happens to be different campuses. Okay. Oh, there she is. All right. Angela turning. And Gonzalez is here. Okay. So I opened up the class early to give you time to go in there and on Canvas. So you give you time to go look at it and download information. So what I want to do is I'll kind of go over the Canvas. There's a lot of the Canvas course itself. And then I go over the syllabus, what assignments you got going on that we do, the do's and don'ts and all that. And then we'll jump into chapter 1. Okay, so let me share the screen with you and go to now my screen will look a little bit different than yours because I don't, let me see if I can do the student view. No. Yeah, so your screen should look something like this for our particular class, okay? And the way I communicate, I can communicate a couple of ways. One, I create announcements. So you'll see your announcements up front. I also use the Canvas email. Now, I don't use my EDU email as much for classes. I monitor the Canvas email a lot closer than I do my EDU. My EDU email address, I get tons of junk mail. So if you want to communicate me quickly and get an answer quickly as soon as possible, do use the Canvas email. Okay, I check that literally, every day, all day, checking it. All right, so obviously you found the Zoom. If you look at the far left panel, you found the Zoom room. It's a link there, gets you to the class here. Now, everything we do here, I will record and then upload it. And so I do have a YouTube channel, and this link here that I've highlighted will send you to the YouTube. So in case you missed the lecture, you missed something, you want to review something, everything we talk about will be recorded. More than welcome to go back up there and view what we did for that day. The syllabus is given here. We'll go over that. Now, this whole class is set up with modules. So if you click on modules, okay, here's the first module. A lot of this is standard information that SCC puts in, and then we have the information that I put in. And so one module is called Additional Chemistry Resources. These are additional resources for you to help you with this class this semester. And we'll go over those when the time comes for the topic. We'll go over these, like build an atom, learning how to balance equations, polarity, and some information about the periodic table. So I put them all, grouped them together here in one module called the Additional Chemistry Resources. Okay. Now, a requirement for SCC, just solely for SCC, is what is called a nomenclature test. Basically, it is an exam, about 20 questions, and it deals with naming compounds. Okay, I'll have more to say about this in a second here, but here there's a module all by itself called Nomenclature Test. There's additional resources in there, and when the time comes, obviously we'll go over it, but it's there for you, okay? But nomenclature is a big fancy word for name the compound. Basically, you have a formula, you may be given a formula, you want to write the name for it, or vice versa. You have the name, give the formula, okay? All right, we'll have more on that in a bit here. So every chapter is written in, has a module, I should say. Every chapter has its own module. And if we look at the chapter 1, well, this, I'm gonna have to adjust that. Nomenclature got in the wrong extra nomenclature there in chapter 1. Anyway, there's an overview of what the chapter is all about, okay? In that module, you also will find the text for that particular chapter, okay? All in PDF format, allows you can download it. You have your own hard copy if you need it. Now, there are videos here. Now, these videos have been pre-made by Dr. Kim Smith out of GCC, and these videos are different from the videos I record here when I talk about that particular chapter. But there's an additional resource that someone else is talking about the topic that I will talk about. Okay, so there's a video for you to listen to Dr. Kim's version of the topic of chapter 1. Also there in this module is a worksheet. In the worksheet, there are practice problems for you. Okay, practice problems that you can do to help you out for the exam that will come later down the road, because we're going to end up with five exams, and these worksheets are very similar, gives you similar work that you'll find in the exam. Okay, now there is homework for every chapter, online homework, and the link to that homework is given there. Okay, more to talk about here in a second about the homework. All right, then I have my it's listed as OER chapter 1 matter 130 OER FFD 1UP. What that is a PDF file of the PowerPoint slides that I utilize, okay? All right, so you will have the PowerPoint slides in every chapter. I've uploaded all the PowerPoint slides for every chapter. And then there is what we utilize for the exams is the lockdown browser. Now, you may have used the lockdown browser for another class. That's if you used it before, then you're all set. If you haven't, you need to download the lockdown browser. And basically, it's a browser in itself and a separate browser that you normally use. And the exams require that you use the lockdown browser in order to take the exam. Okay, so do download it, get it all set up so when time comes, you're ready to roll. And what that does is basically it's a lockdown that the browser doesn't allow you to go to other sites to look things up. Okay, so for the homework, no problem. Use your notes, whatever you need to use, but for the exams, we need to use the lockdown browser. All right, so the instructions are there, so download it, and if you're having trouble, let me know. We'll figure it out. All right, and then there's chapter 2. Again, in its own module, we got the overview, we got the textbook, video, just like, you know, very consistent. Every chapter has all the information you need for that particular chapter. Okay. Any questions at this point? No. No. All right. Well, let's continue with to the far left. We talked about the announcements. We'll get to the syllabus here in a second. We got the modules. If you click on assignments, you can see all the assignments that are there, and you have all the homework, upcoming assignments, and so forth. Every chapter has an assignments. All right, now StudyMate. If you click on StudyMate, this is an additional resource for you, and this helps you. This will help you with respect to naming the chemical compounds. So you're given the formula or given the names. This is an additional resource for you. And what's done, what I did was upload 149 examples of formula and name. And you can use it to help you name the compound. So if I click up here, nomenclature practice, okay, you have a choice. My suggestions is to just stick with the flashcards. The other ones, the flashcards mentioned are pretty good, but the other games, if you will, don't function very well. They don't really support superscript and subscript, but so you're more than welcome to look at it and see what it does. But I suggest using the flashcards. So if I click on flashcards, what you get is this. You get the formula. So you got chromium, Roman numeral 6 sulfite, and then if you do the flip the card, it gives you the formula. Okay, so you can work back and forth, and again, that will help you with learning to write down the names of the compounds correctly. There's iron, Roman numeral 3 hydroxide, and then there's the formula. Okay, vice versa. So it's an additional tool for you. Okay, using the flashcards. Okay. Any questions? Yeah, go right ahead. Unmute yourself if you have any questions. Feel free to ask. And if Jennifer has a question.
Are there going to be study guides?
Yes, in there you would see every chapter has an overview, okay, of that particular chapter, which gives you an outline of all of what we're going to talk about. So that's a very useful study guide to help you with the topics for that particular chapter.
In the test?
Yes.
Okay.
And yeah. Okay. Yeah. Any other questions? All right. Well, let me share the syllabus. So I hope you've had some time to read about the syllabus and read the information. Yes, all right, so the general information given there. I'm not going to go over the whole syllabus. I leave that for your reading. Okay, so information about me, how you can get a hold of me. Again, like I stated, Canvas email is the quickest way to get that. I have access to that on my phone. I do check the EDU, but not as much as I do the Canvas. Again, EDU, I get so much mail from all the campuses that, you know, your stuff will get lost in there. So yeah, do use the Canvas email if you want to get a hold of me, okay? Now, there is a course website, but it's hosted by GCC, and I gave you the link to that. Basically, you are more than welcome to go in there and look at it, but all the information you need, because I'm utilizing the videos and the textbook, I've downloaded everything into the course, so it's not necessary to go to the Canvas to the course website, but you're more than welcome to go and look at it. But there's the link. Okay. There are 29 items dealing with chemistry as per Maricopa Community College that we had to cover, and I list them here 1 through 29. Those are all the topics that we're going to discuss concerning chemistry. It's a lot of topics, you know, and we're giving you the tip of the iceberg, but we will cover it all. Now, as I stated, the textbook, no textbook is necessary. You have every chapter, you have a PDF file for that particular chapter. If you need a textbook or you want a textbook, there is a free textbook for you, option number 2 there. All of our textbooks are open source. It's been created by instructors, and it's free. So you don't need to purchase a $200, $300, $400 textbook. So, but if you need a textbook, number 2, under cnx.org, you're more than welcome to download their PDF. It's a free download for a textbook. You will need a calculator, specifically a calculator that does scientific notation. Okay, scientific notation is nothing more than a means of writing gigantic numbers. So if you purchase one, you don't need anything fancy, expensive, you know, 10, 20 buck calculator. Just make sure that it can do scientific notation, because we will be doing calculations that require scientific notation, because the numbers that we're utilizing are very, very large, and scientific notation allows you to input very large numbers or very tiny, small numbers, okay? So do make sure it has scientific notation capabilities. Okay, now we're gonna have, every chapter has their homework, okay? And there's a total of 15 homework assignments, of which the 3 lowest scores will be dropped, okay? Now the homework is worth 15% of the overall grade. Now, all the homework has 2 attempts. You're given 2 attempts, of which Canvas will keep the highest score. Okay. Now, let me make sure everyone understands this. Your homework will be available until the last day of the class, you know, the last day of the semester. However, they're not limited with respect to time. You have the homework to do, you take whatever time you need to do it, but there is a due date, okay? Now, every homework has a due date. Now, if you don't do it before the due date, what happens is after that, there is a penalty, late penalty, which is 5% per day until you reach the 50% mark. I wrote it here in number 4, okay? Which means that if the homework is worth, say, 10 points overall, well, at the 50% mark, which is at the 10th day, day number 11, the most points you can get is 50% of what it was originally worth, okay? So and you can take that homework and do it all the way to the last day. However, there's a late penalty involved with it. So don't let that happen, and try to knock it out before. Now, you have 2 attempts per homework. Now, what a lot of students have done in the past that works pretty good is they go ahead and they do the first attempt before you even finish that chapter, okay? To kind of give them an idea of what we're going to talk about. And then what happens is a lot of them would then do the second attempt after we went over that particular chapter. Now, the other aspect to remember is I won't make the due date, the due dates are flexible, meaning that I will not make a homework due until we're complete with it, we're done with it, okay? So even though it might be in Canvas saying it is due today, chapter 1 is due today, no, it won't be due today. I just haven't had time to move it over until we complete that chapter. So it won't be due until after we're done with the lecture part, all right? All right, so no time limit on the homeworks, and you have 2 attempts, okay? But they will have a due date. All right, and like I said, there's 15 homeworks, of which 3, the lowest scores will be dropped. Excuse me here, let me catch up with my breath here. All right, now on the Canvas course, there's an additional resource. There are some other homeworks there. You're more than welcome to download those and help you out with the homework. That's not your homework. All your homework is on the Canvas course. The homework at the GCC course website is additional homework, like more help, more examples for you to attempt the homework. And it's good to try to download them because those homeworks are very similar to the homework that you will find in the Canvas course here, okay? I'm trying to give you as much resources as possible. All right. The nomenclature number 2. What this is, now this is only for SCC students. As per SCC requirement, there is an exam, basically 20 questions. What that is, it is pertains to naming of compounds. I briefly showed you the StudyMate. It's along the same lines as the StudyMate. That's why I set up StudyMate to help you out with this nomenclature exam. And it gives you the formula, you write the name, or vice versa. You have the name, give the formula. Now, there's a nomenclature exam all by itself. It's worth 10%. Okay, as per SCC requirements, you got to score at least an 80% to get the credit for this. Anything less than 80%, the score Canvas converts it back to 0. Now, with respect to nomenclature, this is a nomenclature exam. You have an unlimited number of attempts. You can attempt this as many times as you need. It will be due, there's a due date close to the end of the semester. But don't wait until then to finish it up. But 10%, the whole thing is worth 10% of your overall grade. It can make or break a grade that you're set at. What happens is if you're on the border, that 10% can drop you down to a lower grade. Okay, so, but if you're like happy with where you're at grade-wise, and if you don't make the 80%, then you got no problem. You can just give it your best shot. And if it doesn't work, we just have to put a 0 in there. But it can determine if you're on the cusp, whether it's going to push you up to an A or keep you at a B or vice versa. Okay. All right. We do add a 1% bonus if you finish it up before the fourth week. All right. And it gives you an example there. For example, if you're having like a 72% grade, and you don't make that 80% cutoff for nomenclature, it could drop your grade down to 62%, okay? All right, so we're gonna have lecture exams. We're gonna have 5 of them, online exams, which are worth 35% overall grade. And then your final exam, which is comprehensive, covers all the chapters, except the last chapter. The last chapter will not be on the final exam. Okay, and that is the final exam is worth 15%. Now, the final exam consists of all multiple choice questions. Okay, they make up about 60 questions for the final exam. The lecture exams are a combination short answer, matching, and fill in the blank type of questions. Okay. All right. Now, excuse me. That is the, any questions so far? No. All right. Well, obviously, if we were face-to-face, we would be doing experiments, and we won't be doing the experiments are on your time, okay? They are due every Friday. First one will be due next Friday. They are worth 25%, okay? There are 11 lab experiments all online. It consists of viewing videos about things, experiments being done, being observant so you can answer the questions concerning that particular experiment. And of course, there'll be either the questions will be multiple choice, short answer, maybe a paragraph or two. Okay. There'll be 11 lab experiments, and there will be 2 lab exams. And the first one, I believe, first exam covers the first 6 exams, and then the second exam covers the last half of the experiments. Okay. Again, the experiments, like the homework, they do have a due date, and but if you don't complete it before the due date, there is a late penalty. They also will be available until the end of the semester, but if you pass the due date, there will be a penalty involved with it. Okay, and as the others, it's a 5% per day until you reach the 50% mark. The experiments are worth 100 points. And so if you go day number 11, the most points you can get, due to the late penalty fee will be 50% of that 100. So 50 points is the maximum number of points you can get. All right. All right, let's see. The breakdown, the scale is slightly different here in SCC. Normally it's not the standard 90, 80, 70, but it's 88, 78, 65, etc. It's given here. Excuse me. Homework 50%, lecture 5 exams at 35%, comprehensive final exam at 15%, that nomenclature exam at 10%. Overall, lab experiments are worth 25% for the overall grade. Most other places, like at GCC, where I teach the same class, the labs and the lectures are totally different. It is here at SCC that they're combined. And so you got the lab experiments in here. Okay. All right. There's a question there. Let me see. Yes, exams. This question is a good question. You get one shot for your exam, and they are timed, unlike the homework, unlike the experiments and so forth, where they're not timed. The exams are normally about 75 minutes for each exam, and you got one shot, okay? They'll be open throughout the day, and so I always will alert you, okay, the exam's open, whatever time, whatever day it is. Most of the time they open about 7 a.m. in the morning, and they'll be available until about 11 p.m. that evening. So that gives you guys, plenty of time, hopefully, that you can pick a window and knock it out. Give yourself plenty of time to finish it. Like I stated, it's 75 minutes. If it closes at 11, please don't wait till 10:30 to start the exam. because Canvas will kick you out and you won't be able to finish it up, okay? So yeah, you'll have plenty of time throughout the day to pick some time out. Now, for some reason, I understand, you got work or a situation occurs, you need to take the exam maybe a day earlier or a day after. I can go 2 days one way or the other, before or after. So let me know beforehand, okay? Because I have in here the days that the exam will be given, so you know beforehand when the exam is. Please don't wait until the day of the exam and tell me that you need to change it. But so give yourself plenty of time, and we can make arrangements before or after, okay? Attendance. Well, coming to lecture, it's not a requirement. Attendance consists of coming to the Zoom, doing the lab experiments, doing the homework, or any other activities. I do offer extra credit with time activities. So it consists of all of the above. So we're gonna probably jump into the first chapter. The first couple of weeks are pretty, I don't want to say intense, but very active. We got a lot of information we're gonna hit, and so it'll keep you kind of busy. And after that, it kind of slows down a little bit. We go about a semester, each chapter a week, and it kind of slows down a little bit, and now it's a lot more stable. But initially, it's kind of a lot of stuff coming at you. And so, plan on at least, checking in, not attending the lectures, not turning in assignments. That consists as no attendance. So if you have 5 or more missing assignments, I can look at the log and see how often you check into Canvas. If you're not checking in, then I got the option here to do a withdrawal. I don't want to do that. I definitely will send an email, say, hey, I've not seen an assignment in a while, kind of alert you, but if I get no response, then you leave me no option, okay? So just, do your stuff. You'll be good to go. We got no problems. All right. All right. If you need to withdraw, there is a time that you can withdraw on your own. After that, let me know. I'm more than happy to help you out with that. If there's a challenge and things pop up. Right now, in the last semester had a multiple students, get ill and they couldn't keep up with it, so they had to withdraw. I have no problem if you need to withdraw. I can help you out with that. But if you take the final exam, I can't withdraw you. That's one thing, one part. And a lot of students would like to, well, let me do the final, see how I do. I can't do that, okay? So I can't withdraw you. Other information there is for your reading, standard SCC stuff that they want us to put on the syllabus for your enjoyment of reading. Excuse me. Okay, I'm trying to get to let's get to this little aspect here. Canvas, if you're not aware of this, if you look at the calendar in Canvas, they do have a calendar feed. It's basically a link that you can copy that link and then send it to yourself, and it will set up your calendar on your home computer or so forth with all the assignments. So you always know when something is due, okay? Or you can set up Canvas to give you notifications when things are due and so forth, so you won't be ever be surprised. Oh, I didn't know something was due. All right. This is the information concerning the lockdown browser. Take a few minutes to read about it. You will need it in order for you to take the exams, okay? So, all right, we don't use the webcam at all. We're not going to be using the webcam. It's just the lockdown browser all by itself. Now, the thing about that, if like I stated earlier, you may have used it for another class, and if you still have it on your computer, you're good to go. You don't have to do anything, okay? But if you've not done it, this is the first time you use it, there is a lockdown browser specifically for the Maricopa schools. So don't download some other lockdown browser because they won't function with our system here in Maricopa, and that includes the all 10 campuses, okay? So make sure that you get the one, follow the link and get the one from the Maricopa schools. All right, now, excuse me. I have here, and hopefully you can see that. Okay, make sure I can see it on the screen. That is the overall tentative schedule of what we're going to talk about chapter wise, and I broke it down. Okay. Excuse me. Including the labs. The far left column is the lab starting next Friday. There's a safety exercise lab. Okay. The exams, the first one will be February the 5th, and then I got them broken up. You can see here, and then February 26th, and March the 26th, April 16th, and then May 7th, and then our final exam is on the 13th of May, the last week, okay? All right, spring break, March 14th through the 20th, okay? There are 2 days that are written in green here, February the 11th and February the 18th. We won't have a lecture during those 2 days, so I call those study days. And here I will direct you to the videos that we have pre-made to cover whatever we're going to talk about for those particular 2 days. Okay, so I've highlighted those in green. Okay, March the 4th, or is that 10? Yeah, March the 4th. That's a typo there, 10-9. March the 4th is the last day to withdraw yourself if you need to withdraw. Okay. Excuse me. All right. Any questions about this? As I wrote up here, all exams will be available on Saturday. Right here, you see all exams. They'll open up at 7 a.m. Okay, and they shut down at 11 p.m. for that particular Saturday. All right, so there's plenty of time throughout the day to kind of set aside 80 minutes or so of your time. On the average, it takes about an hour for the exams, so the chapter exams. Okay. Any questions? Any questions? All right. Well, all right. Let me stop here for a second. Bear with me. All right. Well, no questions. Yeah, there is one question here. Let me see. Will you get a notification when the lab is complete? Yes. I do get notification when the lab is complete. As far as I don't quite understand, because if I need to grade something, Canvas will notify me that I have something to grade. And yes, that's the notification that I get. Is that the question you had, Edwin? Okay, yeah. All right. Well, I tell you what, let me make sure I got the right one here. No. All right. Okay, let me do. What happened is Zoom has done something to their system. I think they didn't do a very good job of it. They messed it up. So let me see if it's working. Okay, nope, that's not working right. Bear with me here for a second. All right. All right, let me do a quick introduction of myself, give you my background so you know how I got to what I'm doing now. Okay, so my goal here is to help you make sure you get this requirement done and move on to whatever field you're gonna pick. All right, well, let me tell you a little bit about myself, okay? And then we'll do that. If no more questions, we will jump. And excuse my nose. Like I said, I'm at the latter stages of the bug. All right, I'm an Arizona boy. Okay, I grew up in a little small mining town east of here, about an hour drive. If you drive up to Show Low through Globe, Miami, you're gonna pass right through my hometown. So don't blink because you might miss it. Okay, it's a little small mining town right before you get into the mountains there. Okay. Now I am a veteran. 100 years ago, I left Superior, joined the Air Force, was a civil engineer. So I've been doing a variety of different things. Went from engineering into chemistry, which is ironic because my first chemistry class I took, I flunked, totally blew it. Here I am with a doctorate in chemistry, figure that, huh? Anyway, I ended up after my discharge, I ended up in Kansas City, Missouri. That's where my ex-wife was from. She wanted to go home, so I ended up there. I went and got my degree, my undergraduate degree from a university called Avila University. Actually, it was called Avila College until they start offering masters, and they can up their name now. They're Avila University, which was quite interesting because I had a culture shock growing up Catholic. Most of the nuns that I grew up with were from real tough, old school nuns. And Avila University is run by Carondelet nuns. And that was I was like culturally shocked and surprised that I had all these nuns with PhDs in chemistry, mathematics, history, art. I was, wow. Anyway, it was them that got me interested in chemistry, because chemistry, yes, it's a difficult topic, but a lot of times it is offered in a way that it shouldn't be difficult, okay? And the nuns there really are the ones that helped me out to really grasp the concepts of chemistry. And I'm gonna hopefully be able to pass that on to you guys. I continue with my education. I got my doctorate in organic chemistry from the University of Missouri there in Kansas City. And from there, I went, and I'm retired now, but I did my main thing that I did in my field was what is called process and product improvement. Basically looking at the product and finding ways to improve it, or looking at the process and finding ways to improve the process, to improve the profits of the company, obviously. Okay, so I am retired from doing that. I do adjunct at JCC and at Scottsdale. I've been doing that now for a while. And I was a former adjunct for Carrington College before I transferred over to Glendale and Scottsdale. But at Carrington College, I also adjunct as chemistry, math, and physics. Taught math and physics there. So quite a diverse background that I have, I bring here. I worked in construction following discharge. I've done customer service. I've been in the food and retail industry. As a scientist, I also was a software programmer. And after I was all done, I did some caregiving and stuff. So I got a wide variety. Now, the thing about that is that working in industry, I had the opportunity to work with both a lot of lay people and a lot of colleague scientists. And I had to be able to converse layman's terms and convert that into technical terms. And sometimes, like I said, I use a lot of examples, everyday examples to explain chemistry because it's all around us. It really is all around us. And I use a lot of examples, everyday examples. I got 9 kids and 8 grandchildren. So I'm an organic chemist. What can I say? All right. So synthesis. Okay. Well, what I want to do, that's my background. I'm here to help you to complete. I think most of you may be nursing students. That's what happens most semesters, both at GCC and SCC. And I know I may have any chemists there by chance. Any future chemists? Okay, maybe by the end of the semester I might change your mind. All right. No questions? Any questions, comments you have for me that you may want to ask about the course or anything in general? No? All right. Well, what I'm going to do then, I'm going to jump right in. Let me close. Okay. All right. Well, I will begin here. Okay. All right. Well, let's put your chairs up in a upright position. Let's jump in there and let's go. All right. So let's talk about what we're going to talk about. Chemistry. What exactly is chemistry? Okay. Well, chemistry, first of all, it really is all around us. And throughout the semester, I'm going to be giving examples of that, how it's really, sometimes we don't think about it, and how chemistry affects us in literally every aspect of our life. Okay. So chemistry, by definition, is a study of the composition, okay, the structure, the properties, things like physical and chemical changes of matter. Okay. What we do know is this, that all matter around us is made up of atoms. And this is what our thought is at the present time. Okay. Now, we're going to learn about these atoms, and we're going to find out that these atoms are made up of what are called subatomic particles. They're made up of the 3 main particles that we're going to talk about is protons, neutrons, electrons. Okay. And what they do, their weight, they have mass. Okay. Their mass makes up what we call the atomic mass of an atom. There are 118 elements right now, 118 elements that we have, that we know about. They're currently trying to make more of them right now. Okay. But the last 3 that fill up our periodic table were made about 3-4 years ago. They finally isolated them. And there are scientists that they're trying to make more of elements. And I'll mention more information about that as we proceed. Now, these particles, the subatomic particles, protons, neutrons, electrons, they themselves are made up of even smaller material, but we're not going to talk about those. That's beyond the scope of this class in Chem 130. So all matter is made up of protons, neutrons, and electrons. And the thing that really got me excited about chemistry is these crazy electrons. These electrons are extremely tiny in size. Okay, they're very, very small size-wise, especially relative to the size of the protons and the neutrons. And even at that being so small, that has such a big effect on everything. Why certain things are very viscous. Why honey, for example, compared to water, honey is very thick and viscous compared to water that's a lot not as viscous and flows readily. Has a lot to do with these electrons that are around the molecules. Okay. And it's the same electrons that they're running your electronic device right now that you're using, just regular old electrons. Same electrons that give you a bad hair day when you wake up in the morning, your hair is like, boom, you know, or these same electrons that give you a static cling to your clothes and they're hanging on, and that static cling is causing your clothes to hang on to you. These electrons, okay? Well, we're going to talk about those guys. We're going to talk about chemical bonding. And here's the kicker about all this. Of all the chemical compounds that are utilized that we have, that we're aware of, there's only 2 types of chemical bonds. 2 types, imagine it, right? You would think there'd be like all kinds of different chemical bonds, but there's only 2 types of chemical bonds. And we're going to talk about those down the road here, about the type of chemical bonding that occurs. Reactions. These are reactions where we got, compound A going to compound B. Now, normally what happens here is this. All right, we have, let me make sure that, let's say we have A plus B reacts to gives us C plus D. This is what we call chemical reaction. We write that out. We have the reactants, which is the arrow. This is the chemical reaction arrow. To the left of the arrow are called the reactants. Okay? And to the right of the arrow are our products of whatever process occurred. Now, this arrow tells us that something happened. It could be a physical something happened, or it could be a chemical something happened, but regardless of what it is, something happened, and it's saying that A plus B, something happened to it to give us the product C plus D, okay? Now, normally, a lot of times this arrow is a one direction arrow. In this case, it's written from left to right. But it is also feasible at times to have processes that have a double arrow going in the opposite direction, which tells us that this reaction is a reversible reaction. It can go to the right and from the right to left, okay? So this is normally what you see when we talk about a chemical reaction and we write this out. Now, on the periodic table, we have these elements. There's 118 elements, okay? And I kind of think about it in terms of the letters of the alphabet, okay? We got the letters of the alphabet that we know, A, B, C, et cetera, et cetera. We take the letters of the alphabet, we put them together, we make words, right? Well, and then we make words, we put the words together, we make sentences. And from the sentences, we put a lot of the sentences together, we make paragraphs. And the paragraphs we put together, and what do we make? We make a big old book. Well, this is very analogous, very similar here, that we get the elements, we put them together to make compounds. And then the compounds react with each other to have these chemical reactions to make new products. And we have these chemical reactions that we're going to talk about. Now, the reactions that we have, again, we would think that we would just have like 10 billion different types of reactions. And in reality, we only have 6 different types of reactions, given all the chemistry, all the chemical compounds that are out there. There's only 6 types of chemical reactions out there. 2 types of chemical bonds, okay? 6 types of chemical reactions. Right. And we're going to talk all about those with time. Okay? Now, the periodic table and the periodic trends. Well, what do we have here? Well, the periodic table, speaking of that, if you've not downloaded this table, I would, because we make reference to it quite a bit. Okay, this is the periodic table that we utilize. You'll notice that there are 118, the number 118 elements on the periodic table. These letters U, O, that one for number 118, 117, and 115, those are the last three elements that were discovered and isolated to fill up the periodic table. They do have official names now. This table hasn't been updated. So those are all, there's 118 elements that we have, okay? There are numbers, Roman numerals on top. There's A, Roman numeral 1A, 2A, then we shoot across over here, 3A. These letters, these Roman numerals is going to give us a lot of important information, okay? And we're talking about the trend in these elements. Here's one quick takeaway from just looking at the periodic table as it sits, and that's this. These elements that I put in red, they're all in the same column, okay? And guess what? Being in the same column, they all have similar reactivity, okay? And there's going to be a reason why they have similar reactivity. We're going to learn about that. The same with this group right here. They're all in the same column. They're going to have similar reactivity. And I'm just talking about the A elements. Notice the ones, we got another set. They're labeled B. We can't do that prediction, but only for the ones Roman numeral A elements. Being in the same group, they all share a similar property, okay? And they all have similar reactivity. And so keep on going. So we got the same all across the periodic table. Now, if we zoom in, let me clear this up a little bit. If we zoom in, you would notice that every element has a symbol, a letter that represents that element. So number 5 has a symbol, letter B, which represents boron. It has an atomic number on top, okay? And then below the symbol, there is another decimal number, 10.81 in this case, okay? Now go next door to carbon. There's carbon, okay? Carbon has that number, 12.01. That is the atomic weight for carbon. And its atomic weight is 12.01, okay? Its atomic number, it's a whole number, has 6. That's going to tell you some important information. That 6 says I got 6 protons and I got 6 electrons. The elements are made up of protons, neutrons, and electrons, okay? That number tells me I got 6 protons, 6 electrons. And the only difference between element number 5 and element number 6 is 1 proton. The proton defines what that element is. So if I start off with element number 5, boron, and I gain a proton, guess what? I now become carbon, okay? Carbon. But more than that, we will talk at length about that. The periodic table that we utilize, use the one we supply with respect to that atomic weight for each element. Because if you Google it, you're going to find atomic weights that kind of vary a little bit. And the thing about that is that if you utilize a different atomic weight, it might be a little bit off, okay? The answers in Canvas are based on the atomic weights of this periodic table. And Canvas is not AI. I wish it was a little bit better as far as recognizing subtle differences in numbers, but it doesn't recognize that. And you might type in 12.01 in Canvas, right? or let me restate that. You might type in 12.02 in Canvas. Well, Canvas doesn't recognize that subtle difference where it should be 12.01, and it'll count that off, and you may get it wrong. So something to remember when you write an answer in Canvas and you know it's correct, but maybe you inadvertently added a space or you inadvertently added an extra number in the decimal numbers, let me know. I will go in there and look at it and definitely give you credit for it, okay? Because Canvas is not very smart software. It doesn't recognize spaces. We have to train it to recognize all the potential answers it could be. So keep that in mind, okay? All right. Excuse me. Where'd it go?
I have a question really quick while you're looking for that.
Yeah, go ahead.
Okay, so for like you said, the A column, the Roman numeral A column, they have the same property and the same, what was the other part of that?
Oh, they react very similar. They have the same properties, and they had the same number of electrons on the what we call the outermost shell. I didn't mention that at this point, but we will learn that.
Okay, awesome. Thank
So
you.
for right now, just think of it, they have the same properties, and the reason they have the same properties is because they have the same number of electrons in the outermost shell.
Okay, thank you.
Okay, yeah, no problem. All right, so we're going to learn about the periodic table and pick up some what we call periodicity. Okay, things why these elements are put in that periodic table, why they're put in the manner that they're put, why they are in that sequence. Okay, and it all has to do with electrons and so forth. Okay, we're going to talk about an acid, bases, and electrolytes. And I'm pretty sure you're familiar with acids. Your stomach right now, as you sit there, is loaded with an acid, hydrochloric acid. Okay. Now, if, for example, maybe you had too much Taco Bell, all right? Got a little bit of acid problem, acid reflux, what do you ingest? You add maybe a Malox, or maybe you drink some Tums. Well, Tums, guess what that is? It's a base. And the thing about that is you got a base reacting with the acid in your stomach, neutralizing it. So here's your first reaction, acid-base reaction, which when you ingest Tums or Malox or some antacid, that's the reaction that's occurring. You're reducing the quantity of acid in your stomach to minimize the discomfort that you may be having, okay? All right, electrolytes. If you're working out a lot, they ask you to drink, electrolytes. You want to keep those electrolytes going. What electrolytes are nothing more than these elements that have either lost or gained electrons to end up with a charge. What you are drinking is like, for example, sodium. You're drinking the sodium ion, what's called sodium ion, ION. Sodium has lost an electron to give it a charge. And these electrolytes are what are in our body to help conduct electricity, to conduct electrical signals from point A to point B, okay? And so when you're working out quite a bit, not only are, I don't know if you ever noticed, if you work out and you get real sweaty and you go get a t-shirt and you let it sit there and dry. And if you look at that t-shirt's got this white material on it, right? You know what that is the salts you perspired, the sodium, the chlorides that you have perspired, okay? And these are electrolytes that are necessary to get electrical signals. So things like your heartbeat, your muscles contracting without electrolytes, that's not gonna happen, all right? So we're gonna talk about those. Okay, this concept here called the mole, which is not an animal, nor is it a mole, the hot sauce. The mole is nothing more than a number. It just happens to be a humongous number. Okay, very, very, very big. Okay, And we use that a lot in chemistry. And because it's a big, gigantic number, that's where we need scientific notation with respect to your calculator. Being able to do that in learning how to use your calculator and using scientific notation to do calculations. Okay, then they give you this fancy word here, stoichiometry. Okay, it's a fancy word to give you a ratio. All that is a ratio between, in fact, well, let me give you an example of stoichiometry. All right. How many tires does a normal car need? Ask yourself that. Obviously 4, right? 4 tires. If you got a spare in the back, let's just assume just the 4 main tires. The stoichiometry of the ratio between tires of a 4-wheel vehicle is a 4-to-1. I need 4 tires for the vehicle, the car. If it's a bicycle, the stoichiometry for the bicycle is 2 tires per frame. The stoichiometry for a unicycle is 1 tire per 1 frame, okay? And chemistry is the same thing. When chemical reactions occur, there is a stoichiometry between them for the reaction to proceed. 9 times out of 10, it's a simple 1-to-1 ratio. 1A plus 1B gives me whatever product. But occasionally, I might need 1A, maybe I need 2 Bs or 3 Bs, or I may need a ratio of 3-to-2 ratio, okay? And that's what stoichiometry is all about. And it's related to the balancing chemical reactions, the conservation of matter, because when we run a chemical reaction, we have to balance it because of the law of conservation of matter, meaning that if I have 10 elements, if I have 10 carbon atoms in the beginning of the reaction, when I'm done with the reaction, I need 10 carbon atoms, be it in different forms, doesn't make any difference, but they're going to be 10 of them, okay? And that ends up balancing our chemical reactions. But I know it's a lot of information I'm giving you right now. I'm just giving you the introduction. We're going to get into detail all these aspects with time here, okay? Intermolecular forces. This is related to how chemicals react or interact with each other and what gives certain properties to chemicals. For example, earlier I said, okay, I got a cup of honey and a cup of water, and I'm going to do the race and empty them and see who's going to win the race. Well, obviously the water is, right? We know that because we know that the honey is very viscous and it's going to take a little bit longer to flow. Well, and that is because these intermolecular forces. The honey has these forces that where the honey molecules hold on to each other with a greater force than the water molecules, resulting in the honey being a lot more viscous and takes longer to flow. And well, how can we make the honey flow a little bit faster? We heat it up, right? If we heat that honey up, guess what? We break up those intermolecular forces and the honey flows even quicker, right? And these intermolecular forces happen to deal with the type of the interactions that the electrons have with each other. And again, it's interesting is this, of the tons of chemicals out there, and there's only 3 types of intermolecular forces, 3 types, given all the chemicals that are out there. We're going to talk about solutions, okay? And we're going to, touch a little bit on gases at the end of the semester. All right, well, branches of chemistry. Well, like any technical field, any field, regular medical doctors, you got your specialists, right? Pediatricians, heart doctors, muscles, or I should say orthopedic, all the different types. Well, chemistry is no different. My field happens to be organic chemistry. I was synthesizing compounds for a variety of different reasons. Some dealt with medicinal purposes, some did not. Okay, There's different fields. We got inorganic, we got organic. I tell you what, let's take a quick 15-minute break, okay? I got 1:15, let's come back at 1:30, okay? Let's do that, and let me pause. Okay. All right. Well, as I was stating, my particular field is organic chemistry, but there are a variety of different branches of chemistry that are out there. And here's just a tidbit of a few of them. They're out there now. Chemistry question is, why study chemistry? Well, because it's all around us. It really is. I mean, not only the biochemical aspect of it, but everything that we utilize, batteries involves chemistry, electricity, the whole bit here. So there's just some examples of how chemistry is all around us and affecting our lives, okay? Now, scientists, we utilize what's called a scientific method. And you probably use this method unknowingly already, okay? So basically, the scientific method is broken up into steps. First step is you make an observation. You're observing something and you just observe it. For example, let's say you throw soda in the freezer and you notice that the soda bottle exploded while it was in the freezer, okay? So in observing what happened, you formulate a hypothesis. You formulate a guess as to why the soda bottle exploded. And you come to the guess of saying, well, maybe because ice expands or water expands when it freezes. Okay, so that's your hypothesis. So you go and you look through the literature to check and see if other scientists have looked at this process, looked at this observation to find out. Well, let me check this literature as we call it. See if anything else has been published on this. Okay. Well, maybe it hasn't, maybe it has, but maybe they've had some other similar hypotheses or similar things have happened. So what you do is I'm going to continue with my hypothesis, and I'm going to create set up experiments. Okay, you might try different volumes, try different material, and see if the same thing happens. Okay, analyze after you're done with that. Analyze your hypothesis, analyze your guess, and maybe you may need to repeat some experiments just to verify or set up new experiments, whatever the case may be. And then finally, at the end, you draw a conclusion as to what you observed, okay? What is your best conclusion based on the data that you have? Okay, and then fortunately, hopefully, maybe you can get your work published and other scientists would then take a look at it and repeat the experiment. All right, so that's the scientific method. Make an observation, formulate a guess or hypothesis, research it, okay, perform experiments as needed, analyze your hypothesis, and then draw a conclusion. Observations, very, very crucial, okay? As far, if you're like the labs that you'll be doing, it's very important that you observe, make good observations to be able to answer the questions correctly, okay? So some examples of observations here: the color, the solution, clarity, the state of matter. We'll be talking at length about the states of matter, being we're going to work with just solid, liquid, and gas states. There is a fourth state, but we're not going to deal with that one. Okay, matter by definition is anything that has mass. Okay, and that all matter is composed of atoms. Okay, and atoms themselves are composed of subatomic particles that we're gonna learn about. All right, now there are three states of matter that we're going to work with: the solid, the liquid, and the gas. Now, the fourth state is plasma, which is basically just the charged particles. The Northern Lights, for example, is an example of the fourth state of matter, but we're not going to deal with that. We're going to deal only with solid, liquid, and gas. Now, to show these graphically, we have these diagrams. Okay, and you can see that the diagram on the left-hand side depicts a solid. And very ordered, the spheres represent whatever atoms they are, okay? Very ordered and very structured. They're organized and organized in a structured, organized manner, okay? As compared to liquids, though, not as ordered. They're flowing, they move around, okay? That is the spheres here, they move around relative to each other. And in solid phase, no, they're not. They're rigid and they're stuck in position. And then you can see in the gas phase we draw where the spheres are totally separated and there's no very little interaction between the atoms. In the solid phase, the interaction is pretty strong. They're right close to each other, so there's a lot of interaction in there. The liquid, yes, there's some interaction, not as great as in the solid phase, but still, nevertheless, there's some interaction. The point here is this is how we're going to be dealing with how to depict a solid, liquid, and gas with respect to diagrams. Okay. All right, so what do we know about some of the properties of solids? Solids have a fixed shape and they have a fixed volume. Okay. When they are in place, they vibrate. They're sitting there. Atoms. All atoms are moving relative to each other. They're vibrating in place, but nevertheless vibrating. It is not until it is proposed that we get down to absolute zero that atoms completely stop moving. We haven't reached that stage yet. We got very close to it, but we haven't reached the absolute zero. Okay. Solids are crystalline, okay, or it could be non-crystalline in configuration, and they not compressible. It makes sense if you think about it because they're already real close to each other. There's no room to get the atoms to push up against each other any further. Okay, think about this for a second. If we look at these atoms. And if we look on the outside of the spheres here, this is where electrons exist. Okay, our model is this. We have protons in the center and neutrons in the center. And then on the outside, we have the electrons. The electrons have a negative charge, okay? A negative charge. And so this one here versus this one here on the outside, they're electrons. Electrons have negative charge, they repel each other. And so we can't push them any closer together because one, they're already pretty much close to as close as you can get them together, okay? Because the electrons are repelling each other. Compared to being in a gas phase, there's a lot of space in between them. So they're compressible. They can compress when they're in the gas phase, come closer together, but not so much both in the solid phase or in the liquid phase. Can't get them any closer, okay? All right. So they have fixed shape, fixed volume, okay? Not very compressible, okay? And they have what's called density, okay? Now density, here's your first introduction to your first ratio of mass over volume. By definition, density is given to you here in the far right. Density is defined as the mass of the entity divided by its volume that it has. Okay. All right. And so if you can measure the mass, which you can with a balance of some sort, right? And if you can measure its volume, depending on what the material is, you have a physical property of that piece of matter. Okay, so we all have density. We can measure our mass. We can also measure our volume, and we can calculate our particular density. Okay, and it's simply a ratio. just a ratio, no different than say miles per hour, dollars per hour, okay? We're going to be using this concept of a ratio to do all these calculations to get from point A to point B, okay, with respect to calculations. They're nothing more than a ratio of units. We keep track of the units. We can solve a lot of these problems that we're going to work through. Okay, solids, they don't mix very well through diffusion or through osmosis, okay, because they're locked in place, okay, in the solid phase. The liquids take the shape of the container, but they have a constant volume. So, for example, if I have a gallon of milk, it's a gallon, right? And if I got it in a gallon container, I got the shape of that container. But if I take that gallon of milk and I put it into, say, a 55-gallon drum, I still have a gallon, right? But its shape now is the shape of the 55-gallon drum, whatever, totally different shape, but the volume remains constant, okay? Different liquids have different flow rates. They flow differently simply because of these intermolecular forces that they have. For example, the honey and the water example. They're both liquids. The difference is their viscosity, which is related to the intermolecular forces that these molecules have with each other. The stronger they do forces, the stronger the forces, the stronger the intermolecular forces involved, the more viscous the material is. Okay. Liquids are not compressible for the same reasoning behind the solids. They can't compress them because they're already as close as they can get, which is a good thing because liquids allow us to have, hydraulics. Without hydraulics, guess what? You don't have power brakes. You don't have power steering, okay? And it's not fun driving a vehicle, power brakes. You really got to press hard without power brakes. And all that's brought to you by hydraulics in your system. And power steering, that's a fun thing too, without it. All right. They tend to have higher densities than gases, okay? And liquids that are soluble in each other, they will mix uniformly, okay? Now, if they don't mix, they're not gonna mix. Obviously, water and oil don't mix. They're gonna separate, so they don't mix well because of the chemical properties of water and oil. We're gonna learn about why they don't mix, okay? Gases is the key thing. Right now, gases at this point in time do not have shape, okay? They take the shape of the container, okay? They're like liquids. And gases can expand and compress. As the volume increases, the atoms get further apart, and as the volume decreases, the atoms get closer together, okay? They don't have a set volume at this point in time. We're gonna learn in about 7 chapters that yes, there is a set volume, but for right now, no set volume, okay? Very low densities, okay? And generally they mix with other gases very readily, okay? So for example, our air consists of a mixture of nitrogen, oxygen, carbon dioxide, and a variety of different gases. And they exert pressure. Gases exert pressure because these gas molecules are bouncing up against the sides of the container. When you go, if you got a little bit of, if you go and your tire's low on air, instead of the typical 32 PSI, maybe you're 25 PSI, tire's a little low, you go to Quick Trip, fill her up. What are you putting into the tire? You're putting in more matter into the tire, more gas molecules. You put more gas molecules, more of these molecules are bouncing up against the walls. Pressure goes up, boom, you're up at the 32 PSI where you should be with respect to the pressure of your tires, okay? Now, solids have a fixed shape, okay? And they have a fixed volume with respect to solids. Liquids do not have a fixed shape, okay? But they do have a fixed volume. Okay, they do not have a fixed shape. They follow whatever shape the container that they're in, but their volume is constant. Okay. Gases do not have a fixed shape, and nor do they have a fixed volume at this point in time. Okay. Now, some of the physical and chemical properties. Now, here's the difference in between the physical and the chemical properties. When we talk about physical properties, the change in physical properties, this is what happens. We don't change the chemical structure of the compound, okay? When it's a physical change. So let's say we have A, whatever A may be, and it undergoes some process, but we still end up with A, okay? So we still have A, whatever it is, to make any difference here, it's just a general example. We do something to it, and we still end up with A, okay? So this is a physical change, okay? But let's say we start off with A, and we do something to it, heat it, react it with something, and we create something new. See? Now this is a chemical change. Chemical change. Because we no longer have A. We have created something new. It got converted to something different. Okay? See, that's the difference between a physical and a chemical change. A physical change, the chemical structure of whatever that entity was, in this case A, is still A. It could be a solid to begin with, and maybe you heat it up and becomes a liquid. Classic example would be solid ice. We heat it up, becomes liquid. It's still water. It just happens to be in a different phase. Okay. A chemical change, for example, we could take something like a hydrocarbon, gasoline, and we burn it. Boom, it can take propane, your propane for your cookout, or even butane on your lighter. We heat it up, we burn it, it becomes something else. It's no longer butane and propane. It's now carbon dioxide and water, okay? So that's the difference between the two. Now, a physical property, things like the color, okay, odor. I don't recommend tasting it, but they used to taste compounds a long time ago. Don't recommend it. You'll be tasting poison for all you know, okay? Its texture, things like what's called a melting point. That is the temperature in which it starts to melt, okay? Its physical state, is it a solid, liquid, or gas, okay? The density, which is that measurement of mass over volume, that is a physical property, okay? Whether something is soluble in water or oil, that's a physical property. Its conductivity, is it conductive, like metal, okay? Or it's non-conductive. Or whether the materials, how hard it is it a very hard material or is it very soft material? These are examples of physical properties, okay? Okay, with respect to chemical properties, and remember, this is where it completely changes into a whole new product, whole new entity. Is it explosive? TNT, dynamite, quite explosive. That is a chemical property of the TNT. Okay, is it corrosive or is it toxic? Is it poisonous? Okay, or it could be totally inert. For example, gold, pure gold is inert. Gold can sit there underground for thousands of years and come out as shiny as the day it was buried. Okay, so that's the property of gold. Or is it reactive? Certain things are very reactive with the atmosphere and react spontaneously very quickly. Things that it may be a rust, which is a chemical reaction, or oxidizes, or it just decomposes. These are chemical properties, okay? Chemical properties. Now, with respect to physical changes, I'm going to show you stuff here you already know, okay? And we're just defining it for you. For example, when you have a solid going to liquid, we call that melting. Okay, so a classic example would be ice cube going to liquid, an ice cube melting. Okay, when it's a liquid going to gas, well, it depends on what you're doing to it. If you're boiling it, you're heating it up, it's boiling, right? Or it's vaporizing, or it could just be spontaneously evaporating on its own, okay? But it's going from a liquid to a gas. And if it's a gas going to a liquid, we call that condensation, right? Next time you got a cold drink, ice cold drink on the outside, you got liquid forming, correct? Where's that liquid coming from? Well, it's coming from the atmosphere around you. It has water vapor, okay? And as it's all this is a matter of energy. And as those gas molecules come and touch that cold glass, it loses that energy it has, and it brings the molecules together because it lost energy, and they condense, and you got the liquid condensing on the outside of your container. Okay, going from liquid to solid is freezing. So if you continue to remove temperature from the liquid and energy, you go into the solid phase, you cause it to freeze. So these are pretty self-explanatory. You're familiar with them. The one that you may not be familiar with is when a solid goes directly into a gas. Now, it may go through a liquid, but it's going to go through a liquid very quickly, okay? And we call that sublimation. A classic example of that is dry ice. Dry ice is nothing more than carbon dioxide going from the solid dry ice, carbon dioxide, directly into gas. It sublimes, okay? And the opposite of sublimation is deposition. Is if you take carbon dioxide, you run it through this piece of equipment, you cause it to go from the gas, carbon dioxide, into solid or solid dry ice, okay? That's called deposition. Another example would be mothballs. Mothballs, you know, a lot of people use them in their closets, you know, for a variety of reasons, but mothballs go from, it's a compound called naphthalene that goes from a solid into the gas phase, okay? So carbon dioxide is a good example of its property is, it can undergo sublimation and deposition. All right, so a physical change, as I explained earlier, a physical change what's occurring here, the only thing that changes is its physical state, going from liquid to solid. So in this example here, we got H2O. If we look at the formula, H2O, that's water, okay? And we look at the product, guess what? We have H2O. Now, you'll be given examples of chemical structures here that all you got to do is look at the structures, okay? H2O as a reactant, remember, here's the arrow. So on the left side is the reactant, on the right side is the product. And they're both the same, H2O as a reactant, H2O as a product, which then should give you a flag that says, hey, I still got water, H2O, before and after. More likely a physical change. So we go look at the physical state. It goes from a liquid to a gas, okay? Liquid to gas, which is defined as boiling, okay? So we got a physical change here, okay? All right. Now, overall, here's this diagram that kind of puts everything together as we just described. And this is all about energy, okay? Energy. And what is happening here is that we are interrupting by putting energy into the system or taking energy out. We are interfering with the IMF, Intermolecular Forces, the forces of the molecules that with each other. whatever we do to interfere with those forces, that attraction that they have for each other, causes things to go from a solid, liquid, or gas. Notice here the solid's very organized, ordered state. The liquid, not so ordered, and totally disordered are the gas phases. The molecules are all totally separated. And it's a matter of energy. And so we start off with solid and we add energy into the system. We are breaking up the intermolecular forces in the molecules there with each other. We're breaking up that interaction and causing it to go from the solid into the liquid. And if we continue to add energy into it, guess what? We continue to break up those intermolecular forces there, causing the molecules to separate from each other even further to get them into the gas phase, okay? And once we're in the gas phase, we do the opposite. We can remove energy from the system. We subtract energy from the gas phase, and guess what? When we do that, we cause it to condense. So the gas molecules that are all separated, they come and touch this cold surface of, say, the glass has ice in it. That energy then is removed because these guys in gas have high energy. That's why they're all separated. But by removing that energy of the system, you cause the molecules then to attract to each other again and condense. And if we continue to remove the energy from the system, going from liquid, we'll create solid again. Okay, so it is simply just a matter of energy, putting energy into the system and taking energy out and interacting with the intermolecular forces of the molecules, okay? Which is all related to these crazy electrons on the outside of these molecules, okay? All right, so let's clear this up a little bit. All we talked about is all summarized here in this particular diagram, okay? A little bit more on physical changes. Atoms are always moving, even in a solid state, okay? And so what we're doing is this energy I just talked about, it's, to be more specific, it's about kinetic energy. And this is energy of movement, okay? So we put energy into the system, we're causing these molecules to start moving even greater than they normally are, okay? Because of the energy, we're exciting them and getting them to move, okay? And all this here, just a repeat of what I just stated about the gain and or the loss of kinetic energy to go from the different states, solid, liquid, and gas phase. Now, with respect to chemical changes, now it's a totally different ballgame here, okay? Physical changes, we do nothing chemically to the compound, whatever it may be, it still remains whatever it is, okay? With respect to chemical changes, now we got a totally different, we change the formula, okay? We call these chemical reactions. And guess what? All the chemistry involved, there's only 6 types of chemical reactions, by the way, 6 types. We have a whole chapter on that. Okay. So what's happening here with respect to chemical changes, we actually destroy the starting material and create something new, which has totally different properties, totally different structure, okay? A good example would be burning a gasoline. Gasoline here is written in a very generic formula. It's written as CXHX, okay? The X represent numbers. The smallest X for C could be 1, so our smallest one could be this. This is called methane, okay? But the point being that CX is compounds made up of nothing but carbon and hydrogen. These are called hydrocarbons. Hydro for hydrogen and hydrocarbon, obviously, carbon, hydrocarbon, made up of nothing but hydrogen and carbon. So a lot of our fuels are hydrocarbons. There's nothing else involved, nothing but carbon and hydrogen, okay? X's could be right at different numbers. The smallest number is X equals 1 for carbon and H equals 4 for hydrogen. This is methane. That is the smallest hydrocarbon there is. Anyway, combust. Now, here's your second type of reaction. The first type I talked about, an acid base. Remember the Tums and the acid in your stomach? That's an acid base reaction. Here's a second type of the 6 reactions that we're going to eventually talk about. This is called a combustion reaction. We're burning. It's combustion. So one of the reactants necessary is oxygen. Oxygen is necessary for anything to burn. And for us in Chem 130, when you combust a hydrocarbon, which means a chemical that just has nothing, is made up of nothing but carbon and hydrogen, one, you need oxygen, and the only 2 products you make are carbon dioxide and water, okay, for Chem 130. And that's why it's so important that we kind of watch our burning hydrocarbons, because this carbon dioxide is one of the products that get out there in the atmosphere and cause problems out there with respect to, we got to get rid of it. Too much carbon dioxide can be a problem. If we had enough green material to pick it up, it would be great, but our green material is also going down in quantity, so we got to be a little careful. All right, so excuse me. Let me clear this up. So a chemical change, and notice what's happened. The hydrocarbon in the presence of oxygen created something totally new. In this case, carbon and carbon dioxide and water. Notice that remember I said conservation of matter? What we have done in effect is we've taken carbon, which was in the form of a hydrocarbon, and changed it now to have carbon in the form of carbon dioxide. It's still carbon, it's just in a different form, okay? And if I start off with 10 molecules of 10 atoms of carbon, I must have 10 atoms of carbon when I'm done making whatever I make at the end, okay? More on that later on. Okay. Now, what are some indicators of a chemical reaction? When we're observing a chemical reaction, what would indicate that something happened? Well, a couple of things. Obviously, burning. If it's burning, there's no question about it. You are doing a chemical reaction, okay? So it's burning, or you can have, like I used to have an old pickup truck, an old truck, it was full of rust, a lot of chemical reactions on that old Ford I had. Rust, for example, on metal, that's a good indication that you had a chemical process occurring, okay? You could put 2 reactants together and they emit gas bubbles, a little fizzing going on, just like Alka-Seltzer. You know, with respect to Alka-Seltzer, if you look at the ingredients, the only thing they put in there, they got a bicarb, I believe sodium bicarb, and a little bit of citric acid. There's the acid, the bicarb, they react in the water solution once it dissolves, and they cause a bubbling action, okay? Normally there's some fizzing or some bubbling going on, but no heat being given off, okay? A solid, you put 2 reactants together, normally by themselves, they're a nice clear solution, you mix the 2 and you get a precipitate, a solid form. That's a good indication that a reaction proceeded. Or the 2 react together and give off heat. That's another indication that there's a chemical reaction. Or light, you know, a lot of these glow lights that you take and you break the containers of the glow lamps. As you crack them, the 2 reactants meet, they cause a reaction, and one of the products is, what happens is they give off light. And that's a good indication that a chemical reaction proceeded, okay? Or they may change in color. You might have two colorless solutions. You put them together, maybe get a blue solution, okay, or a yellow solution, something. Or you might get an odor, which could be a bad one or a good one. There's a lot of class of compounds called esters, like wintergreen. Wintergreen, these are called esters. Normally by themselves, the two reactants, you get an acid and an alcohol. When you mix those separately, they don't smell very good. But you put them together and you make a class of compounds that smell good, like wintergreen and banana oil. These are good, nice smelling wintergreens. Then again, you get some chemicals you mix and the odor's not that great, okay? So that's a good indication. Here's an example of a chemical reaction. Now it's written in words because eventually we're going to learn to take the words and convert them into write them out in a chemical reaction. For example, it says here, chemical reaction between sodium metal, okay, which is right here, sodium metal, and chlorine gas, okay? They produce salt and then they give you the formula sodium chloride, okay? Now, here's a picture of the sodium metal. This is in an elemental form right here. Sodium metal by itself, it is very, very reactive. In elemental form, shiny metal, very soft, but very reactive. In fact, in the presence of water, it will react violently. It's so reactive. Now, then we have chlorine, okay? Chlorine right here is a gas, poisonous gas, in fact. Some cities in their water treatment, they use chlorine gas to treat the water to get rid of bacteria. It's a very good bacteria treating entity. However, if you live by a municipality that treats water and you see a yellow, golden yellow cloud coming out, they get upwind because they got a gas leak. Okay, so you get a poisonous gas, extremely hazardous metal. You put them together and you make something that you can put on your French fries. Okay, sodium chloride, AKA table salt. Okay, table salt. And the difference, and the only thing that happened, electrons, 2 electrons got transferred from the sodium to the chlorine gas. Okay, 2 tiny electrons. It's analogous to losing maybe 2 things of hair and they totally change personality, like Jekyll and Hyde kind of personality, okay? And that's the power of electrons. 2 tiny electrons were lost from the sodium, transferred over to the chlorine, and now you can ingest the sodium chloride unless you get high blood pressure, and then you don't want to ingest too much because that's a different story, okay? But this is an example of the chlorine of a chemical reaction, totally different properties, got a shiny metal, a gas combined to form this white powder. The power of electrons. All right, so here we have some chemical reactions, and they're asking you to look to determine whether they are physical or a chemical change. Now, obviously, we haven't talked about these formulas. They're giving you formulas already, okay? But that's okay. What we want you to do is to analyze the formula and break it down and see what you observe. All right, let's take the first one. Then I'll tell you what they are here. This is called, you got a nitrogen, and bonded through that nitrogen are 3 hydrogens, okay? So we got NH subscript 3. Now, if we look at the right side of the arrow, guess what? We have NH3. So nothing's happened structurally to the reactant. The reactant is whatever's to the left of the arrow. So structurally, it's still NH3. And so that should indicate to you that I must have a physical change here. Well, let's look at the gas stage, the state. Well, it starts off as a gas and it ends up as a liquid. Okay, so that would suggest that we went from a gas to liquid. Nothing happened to the chemical. It's still NH3. Therefore, it must be a physical change. Okay. And that's what happened exactly. That is an example of a physical change. Okay, let's take a look at the second one, break it down. Okay. All right, we start off with NH3 again. Okay, we go over to the right side of the arrow, and guess what? The first thing that should tell you something's different is that plus symbol. That plus symbol means that we have two products. We got N2 plus H2. Okay, so that would indicate we no longer have any NH3 anymore. Something happened to it. It got broken apart. Now we have, this must be a chemical change because we no longer have NH3. Okay. All right, let's take a look at the number 3. We have this chemical, which is H2O2. Okay. And then we have some process, again, denoted by the arrow, but then we got that plus symbol again as the number 2. That should indicate to you, we got a chemical change. Because we got more than one product now. In fact, we got H2 and O2. What must have happened here is a chemical change. That H2O2 got broke apart to create hydrogen and oxygen. And that is an example of a chemical change. Okay. Let's look number 4. Number 4, we start off with H2O2. Okay. We look to the right of the arrow. We're not seeing any plus, but we're seeing the same formula again, H2O2. So that must indicate that we have a physical change. And let's verify that by the physical state. It went from a liquid to a solid. Okay. So physical change here. Okay. I didn't find it, the last one. Looking at the formula, we got C6H6, which is an indication, remember that CXHX, nothing but a carbon and hydrogen, it's a hydrocarbon. Okay. And we look at the product, again, it's still C6H6, so therefore strongly suggests a physical change. We look at the physical property, we've got a liquid to start off with, and we got a gas to end up with. So sure enough, this is an example of a physical change. Now, that's what we meant by analyzing what's written there. Knowing full well, we haven't talked at all about what these formulas are. Okay, but I'm going to tell you what they are. This one, on the first one, because we're going to use this quite a bit. NH3. Okay. Next time you clean some windows and you have that ammonia odor, that's what that is. This is the formula for ammonia. Or if you had some baby diapers and been sitting there for a while, ammonia. Okay. H2O2. Normally you might think, hey, this sounds like water, right? This is water, H2O. But this is H2O2. If you ever dye your hair or if you cut your finger and you put some of that on there, that is hydrogen peroxide, okay? And then this last one is simply a hydrocarbon, C6H6, that is benzene. But what they are is not important. To take away from this page is being able to analyze the formula you're given, looking at it, breaking it down, and then deduce what's happened to it. Is it a physical or a chemical change? Okay. All right. All right. Elements. We have elements here. There's 118 elements. Okay, only one type of atom only. Can be a single atom like helium, or it could be diatomic. Now we're going to talk about this. Some of the elements, there's 118 elements, but for a variety of reasons, there's 7 elements that cannot exist by themselves. They have to exist partnered up with another element here on Earth, okay? Their stability is such that they're not very stable by themselves, so you gotta have 2 of them together. For example, we call that diatomic elements or diatomic molecules. For example, O2, we always write oxygen as O2 because there are 2 oxygens bonded to each other, okay? They can't exist very well by themselves, at least not here on standard ambient temperature and room temperature. Okay, there are 7 of them, and we're going to learn those 7 of the 118. 7 elements are diatomic. Okay, that means all the rest of them exist by themselves with no problem. Okay, a compound by definition is a combination of 2, at the minimum, 2 or more different atoms. Okay. Now, the diatomic molecules are not compounds because there are 2 or more, they're the same element. When we have 2 or more different atoms, different elements, we have what's called a compound. Okay. And obviously, the term pure is pretty self-explanatory. We have nothing but whatever element or whatever compound we have. It's all by itself. Or it could be a mixture. It could be a mixture of compound. It could be a mixture of elements in themselves. Okay, but pretty self-explanatory with respect to pure and mixture. And we show this quite a bit with respect to diagrams. If we look at mixtures over here, you can see we have 3 different colors. So we got a mixture of 3 different, looks like 3 different elements over here on the far right. The red, the green, and the dark color elements, whatever they may be. So if you look at the next example here, we still got a mixture, but we got 2 where the spheres are put together. Okay, that represents diatomic. They're the same color, the same shape. Okay, so that would represent a mixture of a diatomic element and a monatomic, an element that all by itself is pretty stable. Okay. Compounds, if we go in the pure, on the other side, we got pure compounds over here. And a compound by definition is made up of 2 or more different elements. So we have a diagram here of a picture of water, H2O. It looks like Mickey Mouse there, right? 2 ears, the yellow. Well, that could be hydrogens. The yellows represent hydrogens and the red represented by oxygens. Okay. So 2 different atoms, and we have a compound. And then on the far right, we have an example of 2 different colors of spheres, and that represents sodium chloride. Okay, could be anything, but sodium chloride would fit in that category. And then the elements themselves, when they okay, how about now? Okay, all right, it should go back. I don't know what happened there. We were sitting there and then it just went boom. Don't know if it was me or just Cox themselves. All right, well, let's go back. We're almost done here with this chapter. All right. And so as I was stating here, on the element, the atoms, the diagrams in the far left were showing or demonstrate the elements all by themselves or being diatomic. Diatomic, normally we talk about the word, we use the word molecule. So a molecule of oxygen, which is diatomic, that's the term one would utilize. Occasionally what happens, the term molecule is interchanged regardless of what compound you're using. So, all right. Mixtures, some examples of mixtures, for example, are the metal alloys. Like if you have rings on, gold rings, that's an alloy. Because pure gold, for example, is so soft, it doesn't lend itself well to create jewelry because it's so soft. And things like brass, which is a mixture of copper and zinc, and stainless steel, which you might tend to think is iron, but in reality, it's made up of iron and some other material, a lot of times carbon, and some other trace materials. Sand, graphite, tap water, there's a mixture because the tap water itself has loaded with different ions and so forth. It's not pure. And even the air around us is a good example of a mixture. Some examples of something that's pure could be like pure sodium chloride that you've cleaned up. A diamond, well, it depends on the quality of the diamond. Because they can be actually a mixture with other things. But a diamond is made up of nothing but carbon. And if you're lucky enough to get 100% pure, be nice and clear. And I want you to think about this. You know, if you give it some thought. Here you have a diamond, which is the hardest material on Earth that we're aware of. It's made up of nothing but carbon. And then if you have something like graphite, graphite is a dried lubricant. It's very, very slimy. And it's also made up of carbon. And yet here you have it. You have two materials, a dried lubricant made up of carbon and carbon made up, diamond made up of carbon. And look at the vast difference in the properties of the two. And the only difference between them is they're both made up of carbon, is how the carbon atoms are put together relative to each other. And the diamonds are put together in such a manner that it gives them extreme strength. Okay, and it's all related to the intermolecular forces of the atoms and how they're interacting with each other. To when one end we're making them into a dried lubricant, or on the other side it is made into a hard material. The same thing is true. You can do very similar to polystyrene. You're all familiar with polystyrene cups, very soft, right? Well, polystyrene cups are made up of nothing but carbon and hydrogen. But I can adjust the structure such that I can make that polystyrene so high density enough to create, to be able to be used to make furniture and to make heavy duty material. And just by placing the atoms relative to each other in a certain manner, okay? Anyway, we use a lot of diagrams here to depict an element to the far left. That is a good example of a, excuse me, a diatomic element, because you get two spheres, same shape, same color. And then we have in the center, which depicts a carbon, which is made up of two or more different elements, okay? And then we've got a mixture here, a mixture on the far right, which is a mixture of a compound and two different elements, okay? All right, now, if we look at these diagrams. A obviously is simply depicts an element, specifically a diatomic element. Okay. B is a good example of a compound. Remember, by definition, a compound is made up of two or more different elements. Okay. We don't know specific, we can't really assign something to it. We're just saying this is in general terms, that's an example of a compound. C is an example of a mixture of what happens to be elements. Okay, two different elements. D is an element, again, looks like it's pure, like A is also pure by itself, nothing else involved there. E is an example of a pure compound. There's nothing else in there other than two elements, the clear and the dark one combined to form a diatomic compound. And F is a mixture. It looks like a mixture of, excuse me, two compounds and an element. And also G is another mixture of an element and a compound. And then H is simply an element. And based on the way the pictures are drawn, a certain... Oh, we lost connection again. No, we're back again. All right. Okay. Yeah, today Zoom, and I don't know if it's Zoom or Cox. Cox was kind of acting up earlier today, so let us continue. Maybe I'll speak a little faster so we won't lose it. All right, because we're getting close to the end here anyway. Okay, so H was an example of an element, and the way it's drawn, it should certainly look like a solid, pretty organized and ordered in the way it's drawn. Okay, now let's briefly talk about the elements. As I mentioned earlier, each element has a unique name, has a unique symbol, and a unique number, okay? And normally, they have one letter, some of them just have one letter, which is capitalized. But there are some that have two letters, and the second letter is a lowercase. Now, this is important, okay? Because, you know, the thing about chemistry, like any science, we have to be exact. We just cannot be in general terms at times. But if we were to, let's say we're talking about cobalt. Cobalt has the symbol capital C, lowercase o, okay? That is a symbol for cobalt. If we mistakenly make the second letter capitalized, we're no longer talking about cobalt. We are talking about a totally new compound, which is carbon monoxide, okay? So it's important that we make that second letter lowercase if we are talking about specifically a particular element, okay? So be aware of that. Okay. Now, most of the elements all make their names are English names. For example, H is hydrogen, O is oxygen, He for helium. But some of them have Latin names derived from Latin terms. For example, Pb, which is lead, comes from the Latin term meaning plumbum. Okay. Au for gold comes from the Latin term aureum, which is golden dawn. Okay. Now, be familiar with the first 20 elements, okay? First 20 elements. And that will be from here. So, starting with number 1, hydrogen. Okay, number 2, which is right here, helium. Oh, okay. Then we shoot across to Li. Li is lithium. Then beryllium, so we got hydrogen here. And then we got B for boron, C for carbon, N for nitrogen. And move around a little bit. B for boron, C for carbon, N for nitrogen, O for oxygen, F for fluorine. Quite a difference from fluoride. Now notice this is INE, fluorine. Then we have neon and E, okay? But more on the INE and IDE down the road here, okay? Then we'll go across to Na, which is sodium, Mg, which is magnesium, Al, which is aluminum, Si, which is silicon, okay? P, which is phosphorus, S, which is sulfur, Cl, which is chlorine, okay, INE, not chloride, IDE, chlorine, and then Ar, which is argon, and then number 19, K for potassium, and Ca for calcium, okay? Those are the first 20, and then on top of that, add these for right now. Eventually, we're going to add more, use more and more. So Ag for silver, Au for gold, Pb for lead, Br, notice bromine, not bromide, then I for iodine, okay, and Hg for mercury. Okay, now the physical states. What do we mean by the physical states? At room temperature, or ballpark 25 degrees, and at 1 atmosphere, and this is approximately 1 atmosphere. If you go up higher in the atmosphere, it gets less. Obviously, Colorado will be less. We're up in Denver, it'll be less than 1 atmosphere. But this approximately 1 atmosphere and at 125 degrees. Why do we state that? Because obviously, the state is physical state of these elements will be different on the surface of the moon, right? Simply because it's a little bit hotter. So we got to have a relative point, starting point. And our starting point is at 25 degrees and in 1 atmosphere. There's 118 elements. Of the 118 elements, only 2 of them are liquids at 25 degrees. That is the metal mercury and the non-metal bromine. Okay, those are liquids. Now, the ones that are gases, everybody in group 7 at 8A, not 7, which is, let me go back to the periodic table, and that is in the far right. Everybody here, okay, are gases. They have their own little special name called noble gases, N-O-B-L-E, noble gases. They're called noble gases because they are inert and very unreactive. And they're very unreactive because they have around them the magical 8 electrons. Hence, look at that Roman numeral on top, Roman numeral 8. That represents 8 electrons on the outermost shell. The exception is He, which has 2, but more on that later on. So there are 1, 2, 3, 4, 5, 6, 7 noble gases, okay? Plus, on top of them, we have, here my 7, 8, 9, 10, 11, 12. We have 12 elements that are gases, okay? All the rest of them are solids. Okay, so we got 2 of the 118. We got 2. There's 118 elements. 2 of them are gases, liquids, excuse me. Okay, 12 of them are gases, 2 liquids. That means there's 104 solids. Okay? At 25 degrees and at 1 atmosphere. Now, and we got a table here that kind of summarizes that. You can see here, the ones in yellow are the gases. The 2 liquids, here's bromine and here's mercury, okay? And everybody else is solid. So at a glance, you should be able to determine, hey, is element number is potassium. Potassium? Solid? Yep, sure enough. Okay, carbon. Carbon is solid? Yep, it is a solid. What about fluorine? No, fluorine is a gas. Okay. Chlorine is a gas. So just by looking, you don't really have to memorize each element in specifically, but just take a look at this diagram the way it's written, and you can at a glance determine whether who's a solid, who's a liquid, and who's a gas. Okay. Now, remember I talked about diatomic. Those are those elements that at 25 degrees and at 1 atmosphere here on Earth, they are not very stable by themselves. They must bond with another element of itself. And we call those diatomic elements. Di meaning there's 2 of them, okay, of the same element, diatomic. And there's only 7 of them, okay? And we have this thing here to help you remember which ones those are. Have no fear of ice cold beer or beverage. So have is for hydrogen, for H that is, N in no is for nitrogen, F is for fluorine, O is for oxygen, I is for iodine, C is for chlorine and not carbon, chlorine, and B is for bromine. These 7 are diatomic, okay? Diatomic. Excuse me. All right. And excuse me, we're almost going to be done here with this chapter. Now, we have 118 elements, and they're broken down into 3 types. That's it. We have what are called nonmetals, semi-metals, and metals, okay? Now, the semi-metals, another name for them are metalloids. And what they are is like a mule. You're familiar with a mule. A mule is a combination of a donkey and a horse, okay? A donkey and a horse get together to form a mule. A mule has properties of a donkey and properties of a horse. Is neither one. That's what semi-metals are. They have properties of a metal and properties of a non-metal, okay? Now, we don't have to memorize, again, just every element to determine whether something is a metal or a non-metal, because the periodic table tells us just by analyzing the periodic table, and we have the stair step. This stair step, you see it here? This stair step tells us the metals versus the non-metals. Anything to the right of that is non-metals. Everything to the left is metals. Okay, now put this in long-term memory with respect to electrons, because it's going to come back over and over and over again. Non-metals gain electrons. Okay, always 100% of the time. Metals lose electrons 100% of the time. Okay, and that's important to know, because when we start determining the combination of 2 nonmetals that come together, that equates to a certain type of chemical compound. When we have a metal and a non-metal combined, we have a certain type. There's only 2 types of compounds, okay? And that is determined by whether it's two nonmetals or whether it's a metal and a nonmetal that combine, okay? And so we have to be able to define them, whether it's a metal or a nonmetal, which then helps us to determine whether they gain electrons or lose electrons, okay? And we don't have to memorize this thing. I'm not big on just memorizing each individual one. I'm big at looking at your periodic table and gather information from the periodic table, okay? There's tons of information on our periodic table. We're gonna keep referring to it. All right, let me clear up this mess here. So we got metals, nonmetals, and semimetals. And here is the flow chart, the periodic table to help you to determine the ones in green are the semimetals, okay, or metalloids. We're not going to do a lot of work on those with those, okay? We're going to be basically focusing mostly on the metals and the nonmetals, okay? So the pink are the nonmetals here, the blue are the metals. You can see that the blue, there's a lot more metals than they are nonmetals, okay? And even furthermore, if you think about this for a second, all those metal, the last column, these are the noble gases. They're very unreactive. They won't react to anything. They very rarely make any compounds because they're so unreactive, okay? And so we'll be looking mostly on compounds with, as far as nonmetals, would be like these here, these there, not that many, okay, and some hydrogen, okay, for the nonmetals as far as making compounds. And you think about it, very few nonmetals, and they just make a ton of millions of different compounds. All right. Excuse me. All right, we're getting close to the end. So properties of metals, they tend to have shiny appearance. All right, and they're malleable, that you can stretch them out, flatten them out, okay? All of them are solids except mercury, okay? Their density is pretty high. Their melting point is pretty high, the temperature in which they melt. They're good conductors of heat and electricity, okay? The nonmetals in general are dull in appearance when they're solids. They tend to be brittle, okay? A lot of them are gases. Their density is pretty low. They have a low melting point, okay? And they're poor conductors, but they're much better insulators. That's generally what happens if you're a good conductor of heat. If you're a good, excuse me, you're a bad insulator if you conduct heat very well. All right, so last page here, be able to know the name of the first 20 plus the ones I gave you. Being able to determine any of these elements based on their position, whether it's a solid, liquid, or gas, okay? There's only 2 liquids, a dozen gases, the rest are solids, okay? Based on the periodic table, determine whether it's a solid, excuse me, a metal, a metalloid, or a non-metal. Again, just using the periodic table, and then being able to remember which ones are diatomic. There's only 7 of them. Have no fear of ice cold beverage. Other than that, ladies and gentlemen, I'm sorry I went over it a little bit, but that ends it for chapter 1. Okay, we will continue with chapter 2, obviously, next time with me. If you have any questions, remember, send me email through Canvas, okay? Through Canvas, because I monitor that Canvas email more so than my edu. There are some assignments coming up. Make sure you knock them out. Don't try not to get too far behind, okay? Just kind of, it's a little bit harder to play catch up. All right, any questions? Thank you, by the way. Yeah, it's getting there. That bug is a killer, and I'm fully vaccinated, but it really did a number on me. All right, guys.